Welcome to this explainer. Have you ever actually stopped to wonder how the vast, swirling galaxies way up above us and the tiny beating cells inside us are basically playing by the exact same rulebook? Today, we're going to embark on a really fascinating journey. We'll be traveling all the way from the macroscopic, universal rules of physics right down into the microscopic, bustling mechanics of living cells. It is absolutely incredible how this universe is governed by such beautifully strict patterns at both ends of the scale, and we're going to explore exactly how that works. Here's a quick roadmap for our journey today. We'll start with the fundamental rules of nature and how we measure the physical world before zooming way in to peek into the microscopic world. From there, we'll look at how cells move matter, how they use energy, and finally, the fascinating cycle of cell death. Let's just get right into it. Section 1, the rules of nature. Okay, let's dive in by defining the fundamental ground rules of nature itself. Because before we can look at the tiny building blocks of life, we really need to understand the stage they live on. Physics is, well, it's essentially the mother of all sciences. It gives us the precise tools to observe nature, represent it mathematically, and draw real, concrete conclusions about matter and energy. The brilliant Stephen Hawking once said that physicists don't do this for prizes. They do it for the pure joy of discovering something no one knew before. And that joy, it starts with understanding the basic ingredients of our universe, the literal stuff making up you and me. Take a look at this. There are exactly 7 fundamental quantities, things like length, mass, and time, that make up absolutely everything we can measure in the universe. They are the undeniable bedrock of our physical reality. Any other measurement you can possibly think of, whether it's the speed of your car on the highway or the volume of your morning coffee, is just a combination. It's a derived quantity born entirely from these magnificent 7 foundational building blocks. Section 2, measuring the physical world. So establishing that these quantities exist is one thing, right? But how do we actually go about measuring them in our daily lives? Seriously, think about this for a second. Which device would you choose to measure the precise thickness of a tiny piece of wire? Our human senses are inherently limited. We can't just eyeball a microscopic wire and somehow know its exact diameter. So, throughout history, we've had to invent highly ingenious physical instruments just to overcome our own biological inability to gauge tiny, precise objects. So, the crucial takeaway here is that we rely on a sliding scale of highly precise tools. We start with the basic meter rule, which is great down to about 1 millimeter. But then we step down to the vernier caliper for tricky internal and external distances. And for extremely small dimensions, we use the micrometer screw gauge. Think about how clever that is for a second, translating an impossibly tiny horizontal distance into a much larger, easily readable circular rotation of a screw. It's human ingenuity at its absolute finest. But here's the catch. As we mathematically scale down by powers of 10, moving from the milliscale down into the micro or nanoscale, we run into a serious physical roadblock. Our mechanical tools just hit a hard limit. You simply cannot measure a human cell with a screw gauge, no matter how clever the engineering is. We have to completely change our approach. Which brings us to Section 3, peering into the microscopic. To truly understand life, we have to cross the boundary from the macroscopic measurements of physics and peer directly into the microscopic world. To explore this tiny world, we shift from physics tools to biological instruments. We rely on microscopes, and honestly, they have evolved beautifully over time. From the early basic glass lenses of 17th century pioneers, all the way to the highly complex optical devices we use today, these instruments are our exclusive window into the bustling cellular universe. Now, there is a pretty stark contrast between 2 vital concepts in this microscopic realm: magnification and resolution. You might think just making something bigger is the whole shebang, right? But making a blurry object 100 times larger through magnification is completely useless without high resolution to provide a clear, sharp picture. We absolutely need both to properly see the intricate machinery of a cell at work. Section 4, how cells move matter. Once we have that clear, high-resolution view of the cell, an entirely new world opens up. We can actually begin to observe exactly how these tiny units of life function. Inside complex tissues, like your muscles, your blood, or your stomach lining, cells don't just sit there. They are highly active factories. But how do they know what to do? Well, this is where cell signaling mechanisms come into play.
Cells are covered in tiny receptors, acting almost like satellite dishes. They constantly receive chemical messengers, or signals, from their environment or from other cells. These signals act as specific instructions, triggering an intricate cascade of reactions inside the cell that tell it exactly when and how to transport substances. And in response to those specific chemical signals, transport mechanisms swing into action. This ranges from active transport, which forces molecules against their natural gradient, kind of like pushing a huge, heavy boulder up a steep hill, all the way to completely passive systems like filtration, diffusion, and osmosis. It is genuinely amazing to realize this. Through passive transport, cells can move essential materials around using the zero-energy laws of nature. It perfectly bridges our physics concepts with biology. The cell is just allowing the natural laws of molecular motion to do the heavy lifting entirely for free. Section 5, Energy and the Cell. Because, as we know, nature doesn't give us everything for free. For active transport and those larger metabolic tasks dictated by cellular signaling, the cell absolutely requires a reliable source of fuel. Cells have to consume chemical energy for vital, macroscopic tasks. In fact, nerve impulses are basically electrical signals moving along a nerve fiber via active transport. Even the complex cell signaling pathways we talked about earlier, receiving and processing those chemical messengers, cost massive amounts of ATP, the cell's main energy currency. Your own cells are burning through this fuel right now, literally at this exact second, just to process the visual and auditory signals from this explainer. Moving on to Section 6, the cycle of cell death. Here is where we hit a pretty profound biological truth. Even with perfect energy, perfect transport, and flawless cellular signaling, a cell's life must eventually end. We see this powerful dichotomy in cell death. Necrosis is what we usually think of. It's messy, it's accidental, and it's caused by external factors like infections or toxins. But apoptosis? Apoptosis is highly controlled cellular suicide, and it relies entirely on cell signaling mechanisms. When a cell is damaged or just no longer needed, it receives a specific death signal at its receptors. This triggers an irreversible, programmed sequence where the cell neatly dismantles itself for the greater good of the entire organism. And get this, apoptosis is absolutely necessary for proper human development. When an embryo is developing, we actually have webbed fingers and toes. It is the precise, programmed death signals of apoptosis that instruct the tissue between our developing digits to self-destruct, giving us individual fingers. It brilliantly proves that nature's strict rules govern both creation and destruction. From the vast, measurable physical quantities of mass and time to the microscopic cells that rely on tiny chemical signals to know when to live, work, and ultimately dismantle themselves for our survival, there is a profound architecture to it all. I hope this explainer has shown you how science reveals a beautifully balanced universe, one where the rules of the macro perfectly complement the wonders of the micro. So, I'll leave you with this. What other invisible rules do you think are silently shaping the world around you right now? Keep observing and definitely keep questioning.